next topic, and the next topic is indeed DEFACTO project. So I will be the one presenting, as we've been coordinating from ThedaTech. So yeah, when I was preparing the presentation, I thought to do it like a typical way, but then I decided to improvise a little bit. And as it won't be the last presentation of the DEFACTO, because they gave us an opportunity to present in the RTR conference on February, so that one will be my last presentation of the DEFACTO. So, but yeah. So the thing is that this was started in 2019 when a colleague of mine, Idoia, came to my place and told me, we need to do something with this. And it was this called LCBAT9, and it was pure on the modeling side. So I think it was, maybe there was a previous topic on the modeling, but it was very much on the flow, redox flow, I think. But it was the first topic on the lithium-ion technology on the modeling. So we thought, okay, let's think in a new idea. So we start building this idea, and this is the a picture of it. But obviously, this was not the only idea coming from. The idea was not coming only from ThedaTech. Obviously, we start knocking on different doors, and these doors we had a lot of discussions, and then from the discussion you learned a lot. You modify your idea, and it's becoming a more insightful idea, and so in the end, this discussion came to a consortium, and we were lucky because this project was funded. Because so yeah, we were lucky. We got this water, which is the funding. So on 2020, we started running the project until today, or almost today, because the project will end next month. So and I'm happy now today to introduce what we have achieved within the project. So, but first, for the people that doesn't know anything on the DEFACTO, this is the project concept. So I was saying that the main aspects on the main topic is the modeling. So the center, I would say, is the modeling activities. So we were focusing on not only on cell level, but also on the manufacturing, especially on the electrode fabrication and on electrode and electrolyte filling processes. So the aim was to build different tools to replicate this phenomena, to give more understanding on these processes, and also to link to cell performance and aging. And obviously, it's not the only activity within the project, because there are some development activities on cell level, and then also characterization and testing. Very much, obviously, to understand what is going on in the real cell, but also to fit with parameters to the models that are developed within the project. So, yeah, as I was saying, we were not the only one in the project. We are together 12 partners, and you have here. So, yeah, in this journey, we were with CA, CERT, DLR, UPM, Fraunhofer, UNE, Irizar, ABE, Leclanché, TU Braunschweig, and Sustainable Innovation. So, what we have achieved. First, we have developed 12 models tools. Then I will give a little bit more details. Okay, so 12 models, and 3 coming for electrode processing, and 3 of them coming for electrolyte filling. So, in this picture, you can see the results. So basically, in the electrode processing, they've been mimicking or developing models for different steps, like the dispersing, drying, and calendering, with physics-based models, CFD, DEM approach for understanding in the mixing, for instance, the rheological properties, the drying process, and to extract the porosity of different scenarios in the drying as well as in the calendering steps. And then this turns into a specific microstructure, and this is the microstructure that then has been analyzed on the electrolyte filling. So on the electrolyte filling, there have been another 3 models at different scales from pore scales to electrode and then to cell level, so that we could be understanding how the electrolyte filling should be optimized in order to avoid, for instance, the gas entrapment. So this is one step, and this is one of the achievements. And then also there is another tool, which is basically combining experimental work on the microstructure coming from the data from the CEM, for instance, and even with the simulation results, and they do some stochastical models so that they can reconstruct the more realistic microstructure of the electrodes. And this is also another tool they have developed. It has been developed within the project. So, following the models activities, so there have been another 4 models related to performance. And in here, we've been working very much on the multi-scale approach. More details in the next slide. So we were in the DEFACTO considering the chemistry that was, in principle, more emphasis was the silicon-based anode. So we were very much focused on the mechanical aspects. So the idea was to extract information from the atomistic scales models, then jump to the electrode configuration to understand the swelling of the electrodes, and then go up to the battery cell level, so that this can give us more information on the aging at cell level. So this has been carried out, and this is one of the achievements within the project. And finally, we have also developed on one side one reduced model, and on the other side one fast prototyping tool. And I give you a little bit more details now. So about the reduced model, it's very much focused on the cell model, and it's basically at the continuum scale when you are trying to solve the equations into the 3 domains, so that we can capture also the heterogeneity of all along the cell. It's normally quite heavy computationally talking. So the idea and what it has been developed, it's a reduced model to work on the efficiency of the model. So now we have a much more efficient code so that we can run simulation faster, so we get results in a faster way, especially on the aging, which is time consuming. And then also, we have also developed another approach, very much focused on fast prototyping tool, and it's basically solving equations with neural networks. So, and this can have like 2 opportunities. One is obviously to design a space, because it's once you have trained the data on the model, you have a very fast tool, and this can be used in optimization problem for design space or for design problem, but also can be used for control application, like implementing it into the BMS. So these are the achievements related to the 12 models I was talking about. Another achievement we have done within the project is the advanced optimization loop tool. So basically, because the main purpose of having the tools was to get the maximum information from each of them, and then to provide guidance to cell manufacturers in order to enhance performance. So, but we needed to have, again, fast tools. So it has been developed an optimization tool, which is time and parameter adaptive reduce of the model, and it's available in the DEFACTO project repository. I forgot to say that the previous 2 models, the reduced one and the PIN, are also available in the DEFACTO repository. So yeah, and the thing that so this is more or less on the topic of the models, but I was saying that it's not only about modeling, because we needed to have data. So within the DEFACTO, we needed cells. So there has been a lot of work also there. So some partners were manufacturing electrodes and other cells, industrial scale and prototype scales, and then we carry out testing and then also complementary work on the postmortem to identify certain degradation mechanisms and then fit models in order to have them validated. So this is more or less the summary. So we've been navigating from the current NMC 622 graphite to more advanced at that moment NMC 811 graphite silicon, but even LMNO graphite silicon cells. And this is a picture, these are the pictures from the, for instance, TM results once the cells were cycled, and some micrographs from the again, electrodes harvested from the H cells. So, yeah, and then it was really important to also to validate the models, because this is the way. At the beginning, we were thinking, okay, we will build these models, but we want to take advantage of it. So we need to have them validated against our data. So in this case, we have selected two chemistry cells, and there have been certain work on the validation as well. So, but this is more or less the summary. So on the one side, we've been working on the graphite NMC 622, and there are some pictures coming from different partners. For instance, they've been working on extracting how the calendering process parameters are affecting to the porosity and thickness of the electrode, and then also coupling this simulation tool to a continuous scale tool. They can extract certain parameters from there, like the ionic resistance or electronic resistance. So this is a nice example of combining two different approaches models in order to extract more information. So they've been, I was saying that, so there are some micrographs as well here. So this is the virtually replicated reconstruction of the microstructure, and then this is a comparison behind. The thing is that I cannot point because it's not working, the pointer, but maybe here. Yeah, so this is the virtual stochastic microstructure they have developed, and also the comparison between the results. Also we've been comparing continuous scale model validation, again micro and best meso simulation results. So you can see here the differences between the scales, and so this was a very nice example of how we've been validating the codes that, only some I only bring some examples now today. And then also certain work on the graphite silicon NMC 811, like here that we are validating the model, continuous scale model, on the certain experimental results. And this is, once we have these models validated, we wanted to take advantage of it and then provide certain guidance to cell manufacturers. So in this case, we are solving an optimization problem to enhance energy density. So this is like 7-dimensional graph, but I like very much because you can see the correlation between the parameters. So basically, the idea is to identify which is the best parameter in here, solving an optimization problem in order to enhance energy density, gravimetric energy density, and volumetric energy density. So we are solving the optimization, global optimization algorithms, and then it turns that the best correlations and values are around in here. So this is another way to show the results, and in here you can see that the Pareto front coming from the optimization, and the best results. We have selected this one because if we compute the gravimetric energy density, we are around the target that was expected to achieve in the cold text, that was 300 watt-hour/kilogram. So we are almost nearly here, at least in the C/20 scenario. So but this is another sample that we've been working on. And then And then also finally, not finally, but certain activities, we've been also working on the standardization. So within the duration of the project, there is not enough time to launch a new standard, but we were suggested by a partner that the best way to start working on that area, it was to launch this CENELEC workshop agreement. So apparently it's like the first step on the standardization. So we proposed 2 of them, and these are the ones. So very much on the data that we need for model validation, and also the experiments and characterization techniques to extract the data. So we were proposing these 2 CNWS, and will be published in December, apparently. Yeah. So as soon as we know from the CENELEC committee. And then, finally, we had the target, or when we wrote the grant agreement, we said that we would achieve 6 publications. So in the end, we achieved 13. So we are really happy. Okay. And 3 are still under review, and there are another 3 of them planned. This is the list of the publication. And with this, I would like to thank you all. And I don't know if you have any questions regarding the project, anyone outside the consortium? Maybe. Alessandro, can you hear the audience?
Hello? Now it works.
Yeah.
So my question is the following. You have developed many models. You said a few of them will be released. How will they be released? Will they be part of what has been presented at the introduction in this CDTech environment? Or will it part as Siemens is also a partner? Will it be part of the Siemens tool set? So if we as Umicore are interested, how can we, is it possible to use them?
It depends in which model you could be interested in. So Siemens is not a partner of this consortium, sorry.
Okay, so sorry.
It's a partner of Modalis.
Yeah, okay.
The other one. Yeah, so it depends on in which model you could be interested. If you are interested in the ones that are open, are already available. In the ones that are more related on the electrode and electrolyte filling process, they are not open source. So I guess you should be talking to them directly. Yeah, we could put you in contact. Yeah, for sure.
Okay.
One. Hi, thank you for the presentation, first of all. I'm more practical point of view. So you talk about a lot of models and AI and simulation models. I was wondering about the computational effort and the inference time that you have to deal with during your process. It's an industry point of view.
Yeah. So this was one of the main idea of the, for instance, in the sphere performance, the computational cost, it was, obviously we were aware of that. So this is the reason why we were saying that okay, we will also work on the reduce of the models to somehow solve this difficulty with the computational cost. Then so this is already available and is in the DEFACTO project. If you want to make a trial, it's already available. And then it will depend on the scale or if the specific model. So I know that there are certain models that can last, simulation can last like days or weeks. But I know that they are aware, they've been working very much on the efficiency of the code. In particular, I'm thinking that because yesterday we heard that in the lattice-Boltzmann approach as well, they've been working very much on improving the code to enhance, to save the computational cost. And also, in this particular step, in the electrolyte filling step, they are proposing like multi-scale approach. So obviously, the poor scale is the more heavy, talking about the computational cost. And then if you go to more mesoscale, they have another approach which is much faster. So since the beginning, we have this in mind. And at a certain point, we have solved it mostly, but this is always in mind. Accuracy and efficiency are like the two targets to try to meet when you are developing the models. Yeah.